I don't know. It's up to Yilong. You want to wait? You expecting anybody
Uh,
else? I don't.
no. So
Okay.
yeah, I can start.
Okay, very good. Yeah. So Yilong Wang's going to speak to us today, and we're grateful to have him tell us about modular categories of transitive Galois group actions.
Thanks, Eric. So first of all, I would like to thank the organizers to give me the chance to present our recent work on this classification of modular categories with transitive Galois group actions. So this work is a joint work with Richard Ng and Qing Zhang, and it's available on the archive. So let's get started. Here's the plan for the talk. First of all, I will give us a quick review of modular categories, and with the emphasis on the Galois action on them. And then I will define transitive modular categories and present some very general property or observations that we can make just from the definition. Then I will talk about a very important property of these transitive categories, that is the prime factorization theorem. So using this theorem, we can decompose transitive modular categories into prime and transitive categories. And I will give you examples of prime transitive categories. And it turns out that these are all of them according to the classification results. So at the end of the talk, I will talk about the classification results, and a key ingredient of this and a key technical tool we used to achieve this classification is the Galois symmetry on the SL2 representations associated to the transitive modular categories. So finally, I will give the classification result. Okay, so let's review some properties of modular categories. Modular category is a semi-simple, say, linear abelian category with a finite dimensional Hom space and finitely many simple objects. So I will use this ERC to denote the set of isomorphism classes of simple objects, and I will not distinguish isomorphism class of simple object and its representative, okay, as we usually do. So this is a finite set. Of course, a modular category has to be a monoidal category. It's rigid and braided. So that means we have a tensor product that is associative. And we require, in addition, that the tensor unit is simple. And the rigidity means we have a good notion of dual, but we will not explicitly use this in this talk. So we just put it here. And the category has to be braided. In fact, modular category are non-degenerative braided, as we will talk about later. Modular categories has a spherical structure. The structure enables us to define a quantum trace for any endomorphism that takes value in the endomorphism of the tensor unit. Because we assume the tensor unit is simple, so the quantum trace takes value in the complex number. And in particular, the trace of the identity endomorphism, the identity morphism is called the quantum dimension, or the categorical dimension, or simply the dimension in this talk for the object. The spherical structure and the braiding gave us another structure called the ribbon structure, that is an isomorphism from the identity functor to itself. In particular, for any simple object X, this ribbon structure takes value in the endomorphism of X, but X is simple, so this theta X is a complex number, and we usually call the theta X the twist of this simple object. And once we can take the trace of endomorphisms, we can consider the double braiding between pairs of simple objects. So we can put them in a matrix, and this is the S matrix. In modular category, S matrices are invertible. So we have this S matrix indexed by simple objects. We also can define the T matrix, which is the diagonal matrix with twists on the diagonal, on the main diagonal. I think the defining feature of modular category is that the S and T matrices give rise to projective representation of SL2Z. So we simply assign the generators of SL2Z to S and T respectively. So later in this talk, we will see why I put a bar here, because I will talk about representations without bar later. All right,
here
so,
I have a question.
Yes.
So you can say there's a project representation of SL2Z.
Yes.
But whether SL2Z have a non-trivial project representation or not?
Please say that
I mean, whether every project representation is deformable to the ordinary representation.
Yeah. So at here, I will talk about liftings of SL2Z representation. So at that time, we will see for modular categories, we do have liftings to ordinary linear representations.
Is this
so
is H upper 2 over SL2Z? If that's 0, means there's no non-trivial projective representation.
So I think your question to your question, Xiao-Gang, is yes, because H upper 2 is a torsion.
Oh, they have a torsion.
Yeah, it's a torsion. It's like a Z12 or something.
Oh, H upper 2. Okay, yeah.
Oh, I see.
That's control. That's control if you can lift it or not. It's a torsion thing.
And then there's if you include a central charge in this T, and the representation is a linear or projective.
You can resolve to linear, but it's not unique. There are different resolutions.
Oh,
lifting. It's the torsion. I think it's H upper 2 is a torsion, so that means every projective has a lifting, but the lifting is not necessarily unique. There's some choices to be made.
Maybe let me ask then put that another way. So usually these T matrix here in your definition only contains theta x.
Yes.
Do not contain a central charge.
No. If you want to lift it, you can divide it by normalize it.
Oh, I see. If you include a central charge, you will get a linear representation. If you don't include a central charge, you will get a non-trivial projective representation. If that's a understanding correct?
Sometimes I think the corresponding I think I can say that. Yeah,
I think it's true in general. You know, you have to say in general because there are theory with the central charge 0. So
yes. So it's
a general statement. Yes.
Okay. Thank you very much.
Okay, so modular categories have enjoy interesting arithmetic properties. So for example, Vafa showed that the T matrix has finite order. So in other words, twists of simple objects are roots of unity. And the kernel of this projective representation is long conjecture and proved by N. Schoenberg that the kernel of this projective representation is a congruence subgroup of level n, where this n is just the order of T. And also this field of Q adjoint or entries of the S matrix are contained in the cyclotomic field zeta n. So it is long known that Q adjoint S is in some abelian extension of Q, but here we have a upper bound for this. We have a actually lower bound for this cyclotomic extension.
So I have a question here related to Xiao-Gang's question. So, so there are 3 versions of I think this arithmetic thing, which is you choose the most canonical one, which is the S matrix is okay, only 2 here, but we don't have T. So you choose the S, which have no normalization, so which means have no square root D. So if we throw in the square root D, I mean the upper D, and then the cyclotomic field will change, right? In some time. That's always it's always like twice as much, or
no?
can be worse.
I think it's at most twice because dimension is
least
filling this field.
At least.
At least twice.
At least twice.
At least twice. Yeah.
So I think the level, you have another thing, which is I think Richard is probably the right person to answer. So as we just discussed, the T can be resolved to, using the central charge. There are some choices. And then the order would be different, right?
Yeah, different central charge give you different order.
And then there's a level. If the level also changes, depends on this resolution.
Yes.
So
yeah, the level also change according to the order of the T matrix, right?
Yeah. So that's very simple change, or it's very simple, like it determined by the central charge.
I think
it's
you have more than the choice of central charge, right? You use the central charge. You need to take the third root of the central charge.
Yeah.
So there's a choice here, but the choice also changed the order of the normalization or the lifting.
Yeah. So like at most like a 24n or something, or
I think most, yeah, it is right. At most, I think it's 12.
12. Yes.
Okay, 12. So at most 12.
Yeah, at most 12. You can make it to be n if you're lucky, but generally it's 2n.
Yeah. Okay.
Yes.
Okay. Thanks. Yeah, it's so complicated, but I think this is the canonical choice, the one here, Yilong is talking right now. Okay.
Well, yeah. Okay. So and the third property, arithmetic property, is the Galois action on the set of simple objects. So let me give some details. Since C is modular, all characters of the fusion ring are given by simple objects as follows. If we take any simple object, the character corresponding to the simple object is assigns any simple object to this ratio, and we extend this assignment by linearity, then we can check this using either Verlinde formula or graphical calculus that this is indeed a character or ring homomorphism from K0 C to the complex number. So because Q adjoint S is a abelian extension of Q, so we can consider the Galois group. So I denote that by G of C. So for any Galois automorphism, we can apply it to the whole character. And because it's Galois automorphism of fields, so it becomes another character of the fusion ring. So it has to be of the form, yes.
I thought I already have a problem here. The character is not quite inside Q join S, right? There's a square root thing. Is that true?
Oh, no. The thing is,
you divide it by the square.
If we normalize, we divide both sides, both the numerator and the denominator, by the same thing. So it doesn't matter what normalization you're taking.
What do you mean? So the one you,
they cancel.
Yeah, they cancel.
The
numerator and the denominator are both divided by the same normalization. Something times the square root of the dimension.
All right. Okay,
so,
I think that's okay, good.
Let me ask a simple question. I'm not familiar with this. This chi y is a function of y or function of x and y?
So given a y
is a function of x and y. This ratio.
Xiao-Gang, it's a two variable function.
It's a two variable function, yes.
But you fix one variable.
Yeah.
Okay. So actually chi y do depend on x and y. You just omit this x.
You fix one. You fix y.
You fix y. You look at how this x changes.
Okay. Oh, I see. So chi y is actually is a function of x, but the y is index of this function.
Yes,
exactly.
Yes, we use exactly. We use the simple object to index the characters. Yes.
So it's a non-trivial. So there's a non-trivial thing here, which is when you permute the functions, not a single value. They do permute as a function. That's a non-trivial thing.
That's why I write the whole function here. We make the function into another function, and this other function is indexed by another simple object of C. Okay, so okay, so if we include X, we can write down this equality that is true for any sigma, any X, and any Y. So this in particular induces a permutation action of the Galois group GC on the set of simple objects. Namely, we have a group homomorphism from GC to the symmetric group on this finite set. The reason I put the great thing here is because sometimes we would like to consider a bigger field that contains QS. Then we can consider the Galois group of that bigger field, and that larger Galois group has a natural projection onto this Galois group GC by restriction. So sometimes we will consider this action on the set of simple objects.
I'm a little bit confused. This always fix the trivial thing, right? That's always true for the simple. If you take X equals that.
No. So for example, if you so we will see an example later, but it moves the tensor unit. So we will see an example in the Fibonacci category.
Yeah, that's what I want to remember. But if you look at your formula, put X equals 1 there.
Put X equals 1.
Yeah.
Oh, but the thing is, remember, we are changing the function, right? So I should look at the behavior of all X. I may fix some 1X, right? I can fix X equals 1, but I may change other things.
Oh, I forgot your variable. Oh, sorry. Okay, your Y is the index. So,
yeah, Y is the index of the character.
Okay, it's a good notation. So X is the variable. So I need to look at all of them.
Yes.
Okay.
Yeah, you look at all of X.
Okay.
Yes. So the Y becomes sigma Y. Yeah.
Okay.
Yes.
Thanks.
Okay,
good.
Whether this variable X will be a new simple object of the mapped this modular category.
So we are changing Y into sigma Y. So but X is the value of this function, right?
Variable.
Is the value. Yeah. Evaluated at X. Right.
Yes, but my question is following. Before this function, the index Y and its variable X both are simple objects of the same modular category.
Yes.
After this mapping, what the same states remain to be true.
That's a theorem.
Oh, I see. That's index and the variable still
the same category. Yes.
Yeah, that's a slight non-trivial theorem.
I see. But this modular category can be a different category, but still a same.
No.
They belong to the same.
No, we still we talk about the same category.
Oh, I see. Here. Even the category is not changed.
Yeah.
Okay.
Yes.
Maybe I can add one thing, Xiao-Gang. So this is actually is an important appendix inside the paper of ENO or something, which is you have a function from the fusion ring to U1 complex numbers. And all the homomorphism, kind of the one is given like in this form. It's like XXY if you fix Y. So therefore, we do Galois conjugate, you get a similar function. So it's also picked up by a simple object. So it's a non-trivial theorem that this is true.
Yeah. Okay.
Okay. So this Galois action has many applications in the study of modular categories, especially in the classification of modular categories. For example, in the classification of modular categories by rank, by Frobenius parent dimension, and so on. The number of Galois orbits of these actions are very important, play very important roles. And this inspires us to ask the following question. Can we directly classify modular categories by the number of the Galois orbits? Okay. And the simplest, yes.
Sorry, another question here. Why is it useful? The reason I ask is because when you do this Galois group action, you map same category to itself. You don't get anything new. So
we can. So the thing is, when the rank is low, we can use our known use the known property of permutation group on very few elements. the structure of that group to study the categories. So I think, for example, for a classification of rank less than or equal to 5, I think we can classify them using according to the structure of the Galois group, and then do it case by case.
I see.
Okay, maybe Xiao-Gang, I can answer your question in slightly expanded his answer. So, so the paper you like a lot, I had with Eric and Richard Stang. That's an application of this Galois conjugate. So here, what it means. So if you look at the S matrix and the T matrix, they have a symmetry, which is the particle whole conjugation.
Okay.
Which means the theta the same, the S matrix has a symmetry when you change a particle to a stereo particle. And if you think about this Galois group, you should consider every element in the Galois group is extension of the charge conjugation symmetry. It's some other symmetry bigger than charge conjugation.
I see.
And what happens is that when you have extra symmetry, the ST matrix of your modular tensor category have a lot more symmetries.
I see.
So you are highly constrained. The bigger the Galois group, the highly constrained of your modular tensor category.
I see.
And that's basically the theory will be. If it's a transitive, and I think this is a generalization of a theorem I had with Richard and Eric and other people, which is if you have the Galois group is ZP, P is the rank for prime category, and then there's only PSU, SU2 or something. So,
I see.
So the bigger the Galois group, the more constrained the ST matrix, the modular data, and you pretty much can get the category. So,
so let me say one thing is that this Galois group structure is determined by something like a quantum dimension. So if you know the quantum dimension, you know the algebraic structure, you know the Galois group, and that's further determine ST matrix. Is that something along this line?
Okay, the gamma group is determined by the ST matrix, and the bigger this Galois group, the more constrained the ST matrix, which means they have more symmetry.
I see.
Actually, there's a physical question here, which is we know, for every Galois group, there's a Z2, which is a particle whole conjugation.
Okay.
You can ask the question, what's the other element means physically?
Yeah, that's my question.
Yeah, that's a very good question, which is, what's kind of symmetry physically?
Yeah, what is the corresponding? Okay.
Yeah, there's a physical interpretation of each of the Galois element.
Yeah, okay.
Yeah, thanks for the explanation. Okay, so so we would like to consider a simple case where the Galois action only has one orbit. So this is the definition of transitive modular category. So modular category is called transitive if the Galois group acts transitively on this set. In other words, every simple object is in the Galois group, Galois orbit of the tensor unit. So let me give an example, a Fibonacci category. So I call that Fib. It is a rank 2 modular category with the Fibonacci fusion rule. And the S matrix can be written as follows, where the d tau is the golden ratio. So we can directly compute the characters, the chi corresponding to each simple object, as follows. Chi1 of tau is d tau. Chi tau of tau is the Galois conjugate of d tau. The reason we don't have to include 1 here is because any character evaluated at the tensor unit 1, the value is 1 because it's a ring homomorphism. And you can see that the Galois group now is so we use we are joint Q with the S matrix entry here. So we get Q joint square root of 5 is the field extension, and the corresponding Galois group is just C2 generated by the square root 5 assigned to negative square root of 5. And this map changes d tau to changes detail to its Galois conjugate, so it changes the character corresponding to the tensor unit to the character corresponding to tau. In other words, in our notation, we can write sigma hat of 1 is just tau. So so tau is in the Galois orbit of the tensor unit. So this Fibonacci category is transitive. Okay, so this is the first example of a non-trivial transitive modular category. And we can actually get a lot of basic observations simply from the definition of transitive modular categories. So here I collect some results that we will need. So if C is transitive, then the stabilizer of this action is actually trivial. This is because of a theorem of finite permutation group theory. So which says if you have a abelian group acting transitively on the finite set, then the stabilizer is trivial. Because this Galois group GC is contained in is a abelian corresponds to a abelian extension, is a abelian group. So this is true. Then by the orbit stabilizer theorem, we only have one orbit, and stabilizer is trivial. So the size of the Galois group is equal to the number of simple objects. So in particular, we can see this is a very useful criterion to determine transitivity. We can see the tensor product of Fib and itself is not transitive because the S matrix of Fib tensor Fib is just the canonical product of the matrices. So the Galois, the field extension is still Q joint 5. So the size of a Galois group is still 2. But in this tensor product, the number of simple objects is 4. They're not equal, so this category is not transitive. So this enables us to identify the Galois group with the set of simple objects simply by sending each Galois element to its its image of the corresponding image of the tensor unit.
So you just mentioned that this Galois group is always abelian. Is that right? My understanding.
Yes. This Galois group here, GC here, is always abelian. Yes.
But in general, it's always abelian. In general, it's always abelian.
Yes.
For modular category, yes, but yeah,
modular category.
There are non-abelian extension of the rational number, but we probably will not use it.
Oh, I see.
Yeah.
And is that for is this same thing apply for pre-modular category?
The Galois group of pre-modular category. Well,
you can do it with supermodular. Right.
Yeah,
I would guess yes, actually.
For supermodular.
Maybe that's also abelian.
Actually, Eric, do you guys know?
Pretty special thing to me.
I know. I think it's yes. I think here's the argument.
Yeah. So
here, I think you can argue this way. If you have a pre-modular category, I think you can double it to make it modular.
I see.
I think the Galois group, because the pre-modular live inside the double, so I think it's a subgroup of a abelian group. So better to be abelian.
Okay. Okay.
Yeah. So from this transitivity, we can compute the S matrix. They are only given by the Galois conjugates of the quantum dimension. And actually, from this equality and the modularity of C, we can conclude that if you have something that whose dimension is 1, then it has to be the tensor unit. In particular, the pointed subcategory of a transitive modular category is trivial. So if you have a simple object, then the dimension is an algebraic unit. That means it's an algebraic integer, and its inverse is also an algebraic integer.
Actually, so I have a question now for you for Xiao-Gang. Actually, it's an open question. So I think I remember something. Xiao-Gang, can you hear me?
Yes.
So I remember you wrote a paper I never understood, which is give me a modular tensor category. You can generalize the hierarchy construction to kill all the abelian part.
Almost, yes.
Almost, or you can always do it.
Not completely. When you could have a fermion.
Okay, maybe let's throw out the fermion. So my question would be, this would be a progress in some kind of classification. So suppose you use hierarchy to kill all the abelian anyons.
Okay, yeah.
It would be interesting to know, if, how big is the Galois group? The naive guess would be, oh, they are, transitive. And then you can use his result, but I doubt it.
Okay, that would be.
Yeah, but you can ask the question, how big is your non-abelian core? How big is the Galois group?
Yeah.
Probably pretty big.
That would be interesting. But let me think about it. So actually, our result is following. You try to kill all the abelian anyons.
Yeah.
And but almost. And I think what you get is that you could have some fermion left.
Okay.
And then.
That's not too bad. We call this, it's a spin modular category. You have it's still modular with a fermion. That's the only option.
Yeah, it's a simplification, and it's a way to reduce all these abelian statistics to get the non-abelian core. And what the non-abelian core have this some more special Galois symmetry. That would be very interesting.
So maybe I ask the question: is your hierarchy construction the same as condensation?
No.
And there's the maximal Tannakian subcategory, which is
no, that's not.
I think it's different. It's very violent. It's very complicated.
Okay, all right. Anyway, because in end up you have either no it's either modular or super modular if you do the condensation.
Oh, he's not super modular. He's a spin modular. It's still a modular tensor category. It just has a fermion.
All right.
Yeah, just condensing. It's actually mode out all the abelian statistics. Basically, two modular category, which they only differ by so-called abelian statistics. We say they are the same.
It would be interesting for us to figure out the mathematics. I never really understood what the construction.
Yeah, because there's basically in this classification, all the pointed modular category is equivalent to trivial.
It's an equivalence relation which is very big, which is
bigger. It's bigger.
Yeah, it's like all abelian categories is the same. It's a single class.
Single class, something like that. Yeah.
Yeah, and then it's basically quoting out this.
Quoting out all this class.
It's a new equivalence relation, which is.
And this equivalence is very easy to use. It's very easy to construct, to generate a number in the family. But to classify non-abelian core is still non-trivial. Okay, yeah, go on.
Okay, go ahead.
Okay. So, so the dimensions are Galois conjugate to the Frobenius parent dimension. So these are the largest eigenvalue of the corresponding fusion matrix. It is also the Frobenius parent dimension, like the dimension is also a character of the fusion ring. So, and all the characters of the fusion ring are Galois conjugate. So these are Galois conjugate. So using this results, we can conclude that if you have a non-trivial fusion subcategory inside a transitive modular category, then the dimension cannot be an integer. Because if the dimension of D is integer, then by this Galois conjugation to Frobenius parent dimension, the Frobenius parent dimension of D is also an integer. In this case, D is called weakly integral. And it is well known that in a weakly integral category, all the Frobenius parent dimension of simple objects, the square are integer. But the thing is, the Frobenius parent dimension of this simple objects are Galois conjugate to the dimension. So the dimension square is also integers, but they also have to be algebraic units. And the algebraic unit in the set of integer is just 1 or -1. So if you look at the square of the dimension, it has to be 1. Then we can conclude using this result that the only simple object in this subcategory D is the tensor unit.
So
why
you
do
know,
yes.
I want to just check your statement. So the 1, 2, 3, 4. The fourth property
1,
is
2, 3, 4. Yes.
the fourth property is that for a transitive modular tensor category, the quantum dimension is always an algebraic unit for any simple object.
Yes, because every simple object is in the Galois orbit of the tensor unit.
Yeah.
And I think you have proved in your paper, one of your papers, you prove that anything in the Galois orbit of 1 is an algebraic unit.
Okay.
Yeah.
Probably Richard proved that.
So yeah, we can actually use
what?
Yeah.
I forgot anything.
You forgot anything? Or you don't remember anything?
Remember anything.
In your second property, I have a little bit confused about notation.
Yes.
So the sigma hat is a simple object.
Well, sigma hat is
also was
yes. We use an abuse notation. Yes.
Oh,
so,
I see. So
yeah, if I write it here,
okay.
Yeah, if I write it here, is action on this number.
Okay.
But the number is indexed by the corresponding simple object.
Okay.
So this is just an abuse notation we use to simplify notations. Actually, this should be sigma hat acting on the dimension of mu hat of 1. We just don't want to write sigma hat of 1 or mu hat of 1 every time in the subscript.
Okay, I missed that property. Let me understand it. So this is a equation for a 2-variable function, right? So you are saying that if you have a transitive modular tensor category,
yes,
every entry in the S matrix is a product.
Yes.
Of a quantum dimension times a Galois conjugate of a quantum dimension. So it's always
exactly.
Wow, that's incredible strong constraint. So
yeah, but we can just get this from the transformation of the S matrix. So the characters. So if we look back, so we can just put so in this equality, right? We can put,
I see.
Yeah.
I see.
So
So
we can put 1 for y.
Okay.
Yeah, for 1 for y. So this becomes dimension. This becomes dimension. This is the entry.
Okay.
Yeah.
So that's why you can do it.
But
yeah,
I'm confused about your notation. Because in this notation, the sigma hat is supposed to be arbitrary. But on the other hand, the sigma hat is a fixed Galois action. So this is confuse me.
So you have to look. So you want to determine the S matrix entry for sigma hat mu hat. So you pick sigma hat and mu hat. You want to compute this number, right?
Yes.
Then once you choose sigma hat, you fix a Galois element here.
Okay.
So I know what this is, and then yeah, I compute this number. Yes.
Oh, I see. Now I see. Thank you.
So so yeah, why do we care about this integer dimension subcategory? So let's take a digression to the Milgauss center of braided fusion categories. So let B be a braided fusion category and F a fusion subcategory of B. The Milgauss centralizer of F is the full category containing objects satisfying the double braiding with anything in F equal to the identity identity morphism. Okay, so or yeah, so centralize everything in F. And the Milgauss center of B is simply the Milgauss centralizer of B in itself. By definition, it is a symmetric fusion category, and by theorems of Yilong, such categories are given by finite groups, and in particular, the dimension of the Milgauss center is an integer. So the Milgauss center provides an alternative criterion for modularity, namely a braided spherical fusion category C is modular if and only if its Milgauss center is trivial. And also we need So it's also I would like to mention the double centralizer theorem. If C is modular and A in C a fusion subcategory, then A inherits the braiding and spherical structure from C. So A is a pre-modular category. Yeah. So if you know, in addition, that A is modular, then the conclusion of this theorem says that then the centralizer of A in C is also modular, and C is equivalent to a Deligne tensor product of these two subcategories. This is very useful because using the double centralizer theorem, we can get a prime decomposition of modular categories. So a modular category is called prime if the only non-trivial modular subcategory of C is itself. That means, yeah, if you look for a non-trivial modular fusion subcategory, you can only get C. Okay. And by the double centralizer theorem and induction, so every modular category admits a prime decomposition. I should say at least one, because this prime decomposition is not of modular category is not like prime decomposition of integers. They are not necessarily unique, even up to permutation of prime factors. So now we have enough notations to state and prove the prime factorization theorem. So we are able to show that if you have a transitive modular category, then every fusion subcategory of C is modular and transitive. So every fusion subcategory C is transitive modular subcategory, and the prime factorization of C is unique up to permutation of factors. So here is how we prove it. So if we take any fusion subcategory A of C, it is automatically pre-modular. So we want to show that it's actually modular. So to show it's modular, it is enough to show that the Mueller center of A is trivial, but the Mueller center of A, as we said, has integer dimension, and any fusion subcategory of C which has integer dimension has to be trivial. So from our previous result, so we know that A is modular. Now the situation is you have a modular category and you have a modular subcategory. So we can use the double centralizer theorem to decompose C into a Deligne tensor product of A and its centralizer in C. Okay, I use B to denote its centralizer in C. So now I want to prove the transitivity of A. So I know A is modular. I want to show that A is also transitive. So here is what I do. So because of this decomposition, I know the field generated by S matrix of C is the composite of Q adjoint the S matrix is of A and the S matrix entries of B. And by basic field extension theory, this means the Galois group is a subgroup of the Cartesian product of the Galois group of the small categories, the subcategories. So that means we can write any element in the Galois group of C as a pair of Galois group of A and element of Galois group of A and B. And the way we determine this expression is we just restrict the Galois action on the smaller subfield. So this is how we get this Galois conjugation. So now we can prove the transitivity if we take any simple object of A, then by the transitivity of C, there exists a Galois element of C transforming this this simple object in A tensor B, which is just C, to this simple object. This equality is given by the transitivity of C. But we know that C admits a decomposition like this, so we can also, on the other hand, write this action as sigma hat A acting on 1A and sigma hat B acting on the tensor unit of B. So we have this equality of simple objects in A tensor B. That means X has to be equal to sigma hat A of 1A. That means because I'm taking arbitrary simple object in A, so any simple object in A is in the Galois orbit of the tensor unit of A. So that's why A is transitive. And so that's how we prove the first statement. And the second statement follows directly from a theorem of Davidoff, Milger, Nikschik, and Ostrich. what they said was if a modular category has pointed part, trivial pointed part, so if C pointed is trivial, then the prime factorization of C is unique up to permutation of factors. So this is how we prove the prime factorization theorem. So this gives us one direction, right? If we have a big general transitive modular category, we can consider its prime decomposition, then each prime factor is also transitive. So what about the other way?
Let me ask a question here.
Yes, yes.
If A and B here is both are Fibonacci modular category, then their tensor, the Galois group of their tensor product, it's not the GA times GB, right? Because they have same square root 5.
Yes, yes. So it's
That's
only a
why
subgroup.
it doesn't work, I think.
Yeah, it's a subgroup. It's not equal in general because there's a intersection. So this fields, right? There's an intersection between these fields.
Okay,
so you consider Q adjoint S from A and Q adjoint S from B. There may be intersection other than Q. So that causes the GC to be equal to this, obstruction. Yeah.
But my question is that for the Fibonacci, tensor Fibonacci, that's not a prime factorization, right?
It is a prime factorization, but it's not transitive.
Yeah, it's not transitive. So we have to start with the transitive C.
Oh, okay, so that C is not transitive. Okay.
Yes.
Yeah, because I said from that from this criterion we know this is not transitive.
Okay.
Yeah.
So what's the theorem you are using for the second part?
The second part is a theorem in the Davidoff, Milger, Nikschik, and Austric, the Witt group paper. There they prove that if you have non-degenerate braided, if you have a modular category whose pointed part is trivial, then the prime decomposition is unique.
Okay, so that's already known. That's already known.
Yeah, that's already known. Yeah.
So the non-uniqueness is
because
we call them unpointed
because it's non-pointed here.
Yeah, so I know, but I'm saying is that now we know the non-uniqueness is all because of the pointed part or the abelian part.
Right. Yes. So we can go the other direction. If I have two transitive modular categories there, or even just general modular categories, one is the tensor product transitive. So if C and D are transitive and Q adjoint the global dimension intersect Q adjoint the global dimension of D is just Q, then this category is transitive. Okay, so we can go both directions. So that means if we want to study all transitive modular categories, it suffices to study prime transitive modular categories because we know how to assemble prime transitive categories into transitive modular categories. So an important example of prime transitive modular categories are this PSU at prime -2 level. These are joint subcategory of SU2, P-2. So sometimes, I think in literature, people also call them SO3. So yeah, because I'm giving the data explicitly, so the name doesn't really matter. So let P be an odd prime, and Q be this 2p, a primitive 2p root of unity. We can describe PSU2 for a small p very easily. So when p equals 3, so this is the level is 1, so it's back. When p equals 5, the level is 3, and it's 5 as before. Okay, and both of them are prime and transitive. So now we assume p larger than 5. So the simple objects of this category are labeled by even numbers from 0 to p-3 over 2, corresponding to 0 to p-3 over 2, and x0 is the tensor unit. And this category is prime according to the fusion rule. So the fusion rule can be completely determined simply by this tensor product with the object x2. And it turns out that if you compute the fusion rule, any non-trivial simple object will generate the whole category. So there's not even non-trivial fusion subcategory in this category. So this PSU2 P minus 2 is prime from the fusion rule. And we can write down the S and T matrices unnormalized. They are given by the quantum integers q to the n minus q to the minus n and divided by this difference. And the twists are given by this quadratic power of q. And because we are given specifically, explicitly the S matrix entries, we can directly prove that these categories are transitive. So in particular, if we have any simple object corresponding to these numbers, then 2k plus 1 is co-prime to 2p. So by Galois theory, there exists a Galois automorphism actually in the larger group so this Galois of q adjoint 2p root of unity is actually larger than the q adjoint s, but we can use it because of this natural projection. So we consider this Galois action that sends q to the 2k plus 1. Then we can do a simple computation on the on this quantum integers. We can write down the formula that we gave at the beginning. So we consider the transformation of J0, 0, 0. That means we want to consider the transformation of the character corresponding to 0. And it turns out that for any j, you can change the variable j. After the Galois action, you get something that corresponds to the character of the k object. So in other words, this Galois action on this object is x2k. So remember x0 is the tensor unit, and k, we take k to be arbitrary simple object. So any simple object is in the Galois orbit of 1 of the tensor unit. So it is a transitive and prime modular category. And the thing is, we not only can consider this PSU2 theory, we can also consider Galois conjugates of the whole category.
So, question: as an abstract group, the Galois group is just a Z P minus 2, right?
As a Galois, as an abstract group is ZP, and you have
Z is the Z the rank, right?
Yeah, ZP cross. Can you say that again? So the Galois group of this Q adjoint 2p root of unity over Q is isomorphic to Z mod 2p units in Z mod 2p. So it's Z mod 2p cross.
Z mod 2p.
The unit
isn't cyclic, or it is?
No,
it is cyclic.
Yeah, I'm saying,
cyclic. Okay.
It doesn't matter. So whatever the rank, it's just Z, the cyclic group of that number. Is that correct?
Yeah. Well, that is only for the larger for the larger cyclotonic field. Actually, we have to consider a real subfield of that. So because the S matrix here is real, so we are not considering the whole the actual Galois group GC. It's not this whole group. It's
okay, that's fine. But I'm just asking you as an abstract group what it is. Because I know for Fibonacci, it's a rank 2, it's a Z2. So I'm guessing that that's always true.
Cyclic group of order P minus 1.
No.
Yeah.
P minus
1. Cyclic group of P minus 1. Yes.
P minus 1.
Yes.
Okay, it's P minus 1. It just, well, that's just the rank. Oh, yeah. Okay, so what I said is correct. It's just Z, whatever the rank. P minus 1 is the rank.
P minus 1.
If P is 5, then this guy is 4.
No.
Oh,
This one is P minus 1, but the real subfield is P minus 1 over 2.
Divided by 2.
Yeah, divided by 2. It's cyclic group P minus 1 divided by 2.
Yes.
And that is the that is the rank. Yes. That is the rank.
Okay. Yeah.
Yes.
So in particular, you don't see things like the Klein 4 group and rank 4 and that kind of.
No.
Yeah. I think that's what I remember. Just the simplest thing, like you go 0, 1, 2, 3, 4, 5, then go back, right?
Yes.
Okay.
Yes.
Okay. Yeah.
Yeah. All right. So we can also talk about the Galois conjugate of this category. If you don't like the this presentation, you can say, okay, I can just pick another Q. I change Q into Q to the L, where L is co-prime to 2p, and I can construct a similar another category with the same fusion rule. And those categories are also prime and transitive. We can use similar techniques to prove that. So here is a theorem of polish and color that we will use in our classification results. It says that if C is a modular category that has the same fusion rules as this PSU2 at p minus 2, level p minus 2, then C is actually equivalent to a Galois conjugate of it. So it may not be exactly this category, but it's a Galois conjugate of it. So we can change the Q to get the category. So in other words, if we want to show that, in fact, our result says these are all the prime and transitive modular categories. And the final step of proving that is what we find the fusion rules of prime and transitive categories are the same as one of these categories. So we can conclude our result.
Hey, Yilong, in case you use this for your job talk, I think there's another H in frolic.
Oh, another H? Oh, okay.
I think so.
That's very important.
Sorry.
He's very picky, so you will be in trouble.
That will be problematic.
Oh, okay.
Your job is gone.
Yeah. Thank you for the. Yeah. My bad. Sorry.
No problem.
Okay. So finally, I'm able to talk about the classification. Probably I will not have time to go through the details. So what the only thing that I want to say now is the technical tool that we use here is the SL2Z representation that lifts the projective representation rho bar of C. So as we as Zhang said before and Richard said before, there are 12 such lifts. So according to your needs, you may choose one or another. And it turns out that for us, probably we can show that there's always a lifting so that the level is preserved. So in this case, we may not use the S divided by square root of dimension and T divided by a third root of the central charge. But yeah, so any such linear lifting is called a representation of SL2Z associated with the modular category. And
so there's a question. What's the reason you use the bar? So
I just used the bar for the projective one.
No. You somehow you don't want this to be the representation. You want this to be the representation of the bar theory or something. Why bother to call this the bar? You know what I mean? This is a modular tensor category. You have a representation rho C, but you don't want this call this rho C. You want this call this rho C bar. Why you want to call rho C bar?
I think at that time I just want to use this to denote I'm considering the projective representation here.
Okay. I think
this is the projective representation.
Okay. I think I understand the question. Okay.
Yeah.
Okay. I know what's the confusion. So I was thinking your bar means complex conjugate. Your bar is not. Your bar is a quotient.
No, it's your quotient. Yes, exactly.
Okay.
Yes.
Well, I think if you are talking to physicists, you better to put a parenthesis, like a square. Okay. It's like an equivalence class is rather than it's really equivalence class. It's not complex conjugate. Okay.
Yeah.
That's better.
Some bracket maybe.
Yeah, it's a bracket.
Okay.
So for me, I look at it, it's like, oh, why you want to call this the complex conjugate?
I see your point. Okay. Yeah. This means the
it just means the projective
projection.
one.
Yes. Projective
okay,
one,
good.
Yes.
I think a tilde or bracket would be better.
Yes, indeed. So this linear representations also have arithmetic properties that I will go over very quickly. So first of all, the order of the normalized T is between n and 12n. as Richard has said. And also this any lifting has congruence kernel, and this Q unnormalized S is contained in the normalized S, and this normalized S is contained in Q adjoint zeta n, the zeta of the root of unit, small nth root of unity. And then we can consider the larger, so actually this Qn should be this field, Q adjoint zeta n. So this is a larger Galois group. This larger Galois group can act on normalized S and normalized T, and the transformation is given as follows. This normalized S is a sign permutation and composed with S, and the transformation of T is actually related to the square in the Galois group.
So Xiao-Gang, I just want to mention, this is exactly the formula we are using to classify the low rank.
I see, okay.
But you can see that if you have a lot of sigma, and then the S matrix entry from the left and right are related by up to a sign. And the T matrix is order 2. So you get a lot of, relations between different S matrix entries.
But how do you determine what kind of Galois group you have?
You have to, that's how it goes. So suppose you want to do rank n.
Yeah.
So it's a abelian subgroup abstractly of the permutation group of Sn.
Oh, I see.
And then you can list, list them.
That's a determine, that's a limit your possible choice Galois group.
Exactly. And then you have to Z2, there are many different realizations of Z2, but still it's a finite number. And then you play with, how many variables, is unknown inside your S matrix. So
if you have a higher programmer, can you do even bigger rank?
Yeah, there are people doing rank 6, but it's much harder.
What I try to say is that you, by going this way, you basically reduce problem to a finite problem, a finite search for every rank, right?
Yes.
Okay, yeah.
Mm-hmm.
But it's not necessarily solvable.
It's grow very quick.
Yeah, it grows quickly.
Yeah.
Thank you.
So one thing that we can show is that every representation of SL2Z associated to a transitive modular category is irreducible. Actually, we do that by analyzing the transformation of the normalized T. So here are some technical details because I think I went over time, so I will just omit that. And the key point is so the degree of the linear lifting is this phi2n, which is the number of squares in the unit of Z mod NZ. It turns out to be too small. That means if your degree is this and you are a representation of SL2 Z mod n, then you have to be irreducible and you have to be of this form. We can even write down explicitly what representation is if we know the normalized T. So and these etas are, you can view them as liftings of a Galois conjugate of this PSU2 theory. So given by science and yeah. So now we can prove the classification of prime transitive modular categories. So if C is non-trivial prime transitive modular category, then C is equivalent to a Galois conjugate of PSU2 P minus 2 for P larger than 3. And the idea of the proof is, so the important ingredients in the proof is we use the type of row as in the last slide, and we use the Verlinde formula and unitarity of S to conclude that if you are prime, then your order of T, your normalized T can only be a single prime. Then, because we know what happens to row in a single prime case, we are able to use the Verlinde formula again to determine the fusion rules. At the end, we use the result of Froelich and Köhler to conclude that this category has to be one of the Galois conjugates of PSU2 at P minus 2 level. So together with the prime factorization theorem, we obtain the full classification of transitive modular categories. So here it is. If C is a non-trivial transitive modular category, C is equivalent to a Deligne product of prime transitive modular categories in the last slide with distinct orders of T. So when we assemble different prime transitive modular category. If we still want to get a prime one, then we want some trivial intersection property, and that is guaranteed by the distinction of the order of T. And that's it for my talk. Thank you for your attention. And thank you very much for the questions.
Thank you. Thank you.
Thanks.
So